Okay, looks like we are live.
Maybe while we're waiting for everyone to get joined, you could put in chat where you're from. Just see like all the geographic diversity we have here.
Okay, where is chat?
Oh, it's on Twitch.
Oh, I don't even think I've got a link to the Twitch stream. Also, it seems like we're having issues getting Maria and Delbert on. Maybe the password is single use, the link that we were sent.
It shouldn't be. Actually, Peter, could you take care of that while we get started with the session?
Could you check the waiting room? I think as host, you have to.
Maybe, yeah. Let me see. How do I open waiting room here? Okay, maybe I can make you a host temporarily, and then. Okay, okay, let's get started with the first part of the event. So yeah, welcome. Hello, everyone. Welcome to Microsoft Intro to Quantum Computing workshop. We're really excited to be collaborating with Microsoft over the course of this hackathon. You know, they have really designed a really exciting challenge for the 24-hour hack this weekend, and we look forward to seeing all the exciting results that will come up. We do have a series of workshops to get you up to speed for the hacking event. So in the workshop today, we'll have an intro to quantum computing, two intro to quantum computing talks, but later we'll also have a more technical workshop on the Microsoft Quantum Development Kit, and that's slated to happen on Thursday, April 8th from 11 to 1 p.m. Eastern Time. So in just a sec, I'll hand over to John from Microsoft so we can get started, and then Delbert will be joining us later for the second session. We'll do a Q&A session at the end of each talk. So during the tutorial, please post any questions you have in the Twitch chat. I'll be monitoring it, and then after the talk part of the tutorial, I'll ask some of the questions to the speakers, depending on how much time we have. Right, so today we'll be hearing from Jonathan Skerritt and Delbert Murphy. So Jonathan is a senior consultant and quantum ambassador at Microsoft, and Delbert holds the roles of cloud solutions architect, data scientist, and quantum computing community leader at Microsoft. So without further ado, it is my pleasure to introduce John, and please join me in welcoming John for his talk.
Hi, everybody. I will start off by welcoming everybody to the kickoff session of the Quantum Coalition Hack, where we'll all hold hands. We'll wade into the shallow end of quantum computing together. My name is John Skerritt. I'll be strapping on your floaties, and later on, my esteemed colleague Delbert Murphy will throw you all into the deep end with total disregard for your quantum safety. I'll start off by saying that I am not a physicist. I am a software developer by trade. I've been interested in quantum computing since I was in my 20s, and I started picking up on Q# about a year ago. So let's get into the session. First, we're going to start off with the basic concepts of quantum computing, which are our qubits and gates and measurements. And then next, we're going to talk about quantum random number generation using quantum computation. And then to wrap up my half of the presentation, we're going to use that knowledge to generate our own quantum random numbers by stepping through a Q# tutorial using Jupyter notebooks. After that, I'll hand you all off to Delbert, who will introduce you to quantum oracles and algorithms with a specific focus on the Deutsche algorithm. And then we'll run through another Jupyter notebook and finish up by talking about multi-qubit systems and entanglement. So what are we going to learn today? We are going to take a little recap of the linear algebra that's needed for quantum computing. We'll cover a couple basic concepts like learning how to generate truly random numbers. And we'll cover only what's necessary in order to talk about the quantum algorithms that we want to implement, because quantum computing is a vast topic and we're not going to be able to explain all of it in the time that we have. We'll talk about a very fundamental concept of quantum oracles, which we use as one of the ways to define a quantum speedup. And of course, we'll talk a lot about implementing algorithms in Q# and the ways that these concepts are reflected in the programming language. So our first step is the basic concepts of quantum computing. The most basic concept, of course, is the unit of computation. In classical computing, our smallest piece of information, our unit of computation, is a bit, and a bit has a state. It's a very simple state. It's just a number, 0 or 1. In quantum computing, our units of computation are qubits, short for quantum bits. Their states are vectors, and this is where it gets interesting. We have quantum states that mimic the classical values 0 and 1. As a corollary of this, we can simulate any classical computation on a quantum computer. It's just that we don't really have a reason to do that, because we want to do purely quantum things on a quantum computer since that's what it's good at. So those states that mimic 0 and 1 are called basis states. They're column vectors. The 0 state is a column vector in which the first element is 1 and the second is 0. The 1 equivalent is the other way around. The first element is 0 and the second is 1. The notation that you see this 0 and 1 enclosed in the vertical bar, that's called Ket notation. It's basically used to denote that we're doing something quantum and not just discussing vectors. It becomes much more useful when we start talking about multi-qubit systems, as Delbert's going to do later on. So for now, just think of them as variable names. It's a quantum variable 0 and quantum variable 1. The states that don't have a classical variant are called superposition states. Those are column vector states in which neither element of the vector is 1 or 0. So we can see that the superposition states are linear combinations of basis states. If you remember the basics of linear algebra, you're going to remember that vectors are linear. You can multiply them by a scalar number, you can add them, and this is the same as multiplying each element of the vector by a number or adding up the vectors element-wise, respectively. This is actually the first lesson of today's session. if you don't know this yet. We'll say that the superposition state means that the qubit is, we'll never say that the superposition means a qubit is in 0 and 1 simultaneously. It's not the right way to think about it. The qubit is in a specific state that is a linear combination of the 0 and 1 states. And there's a plethora of such states. It's also not correct to say that there's just one superposition state. So superposition states are all states that are not basis states, and there are a lot of them. Now, the coefficients of the superposition states can, in general, be complex numbers, but that's a little too deep for us to dive today. The algorithms that we're going to discuss today, we don't need complex numbers. We're going to stick to just real numbers. And here is how you can visualize quantum states. The vectors that represent quantum states have to be normalized, which is to say the sum of absolute values of the components squared equals 1. That's a complicated way to say that the radius of this circle here is 1. So geometrically, this means that the two numbers have to belong to a unit circle. Here we see that the 0 state, the state in which the first component is 1 and the second component is 0, is on the horizontal axis. And the 1 state is on the vertical axis. And any point on the circle corresponds to some superposition state. For example, this state here that's kind of between 0 and 1, that's known as the plus state. And you can see that the amplitudes here are 1 over square root 2, 1 over square root 2. If you square those values, then you get 1/2, 1/2, which are the probability amplitudes that you would end up in the 1 state or the 0 state. We're going to use this unit circle visualization a lot throughout the course of this. Now, how do we represent qubits in Q#? It's one of the topics that people often have questions about. So let me spend a minute discussing this in slightly more detail. Physically, we can never observe the state of the qubit. We don't get this nice vector state representation that we've got down here at the bottom right. This only happens in simulation. And when we manipulate the qubits, we also don't send it instructions like go from this state to that state by multiplying yourself by this matrix. It's not done in physics. Instead, we manipulate qubits by applying gates to them. If anybody is familiar with a black box system, that's kind of sort of what qubits are. We can't really peek at what's inside of them. All we can do is apply operations to them and then measure the outcomes. And this is the representation that Q# uses. So in Q#, qubits are a data type that's kind of similar to a software object in object-oriented programming languages. The qubit has an internal state, and you don't really necessarily have access to every component of that state. In Q# you don't, but rather you can modify the state and get access to some of the information about it via special getter operations. Here you can see the example of a Q# program. Very, very simple, very, very easy. We're going to be working with some Q# programs later on. So when we allocate a qubit here, the syntax is the same as defining a variable. We allocate it and it always starts off in state 0. That's important. So the mathematical notation of qubits describes qubit states. In the previous slide, I was mostly focusing on the vectors that represent qubit states, but this isn't really what's happening in the physical system. Remember that quantum computing has to reflect the behavior of quantum systems. It is slightly abstracted behavior, but we still want it to reflect the things that we can actually do with our physical systems. And we want our programming tools to reflect those same capabilities. It'd be very inconvenient if our programming tools allowed us to do something, say in simulation, that we couldn't physically implement on a device. And vice versa, we don't want our program tools to restrict us from doing something that we can do on a device. We want our tools to not just reflect what's going on physically, but also give us a little bit of help if they can. This is why when running on a simulator, either in the cloud or locally on your computer, we take advantage of the fact that the simulator actually knows the internal state of the qubit because it simulates it. So there's a very helpful function called dump machine illustrated on line 7 that allows you to peek at the state of the qubit to see where your program is headed. You're not going to be able to get the same capability when you run on actual quantum hardware. However, if you're just learning the basics of quantum computing, or if you're running your program on a very small instance of a problem and you want to see where you went wrong, try to debug things, it's very helpful. So what this code snippet does is it allocates a qubit and immediately sees what state the qubit is in by using dump machine. And if you do this, you'll get the basis states, and you'll see that the amplitude of the 0 state is 1 and the amplitude of the 1 state is 0. That's exactly what we've promised, that the qubit is initialized in the 0 state. That's all we're seeing here. Now, the next thing we want to do with our qubits is to change their states. And again, if we draw some parallels with classical computing, in classical computing, we had bits and operations on bits. The most primitive operations are Boolean logic operators. All more complicated calculations can be represented as combinations of Boolean logic operators. And those Boolean logic operators are described by truth tables. For example, here's the truth table for a single bit operation, the NOT gate. You can see that it converts 0 to 1 and 1 to 0. In quantum computing, we use vectors. And the best way to modify the state of a vector is to multiply it by a matrix. And this is what quantum computing does. So since single qubit states are vectors of length 2, our matrices that represent single qubit gates are defined as 2 by 2 matrices. And the effect on the qubit state is defined using matrix multiplication. On the bottom right of the slide, you can see that we're applying matrix A to state psi. The first thing on the line is the Ket notation, which then corresponds to the multiplication in the center, and then you get the product on the right. So let's see what kind of operations there are classically and what operations there are quantumly, because there is not a one-to-one mapping. Classical operations on 1 bit, there are only 4 of them. There's the identity operation, which really doesn't do a whole lot, doesn't change the state of the bit at all. There's negation, which changes the bit to the opposite one. And then there are constant 0 and constant 1 operations that either always output 0 or always output 1, respectively. On the right side of the slide, you can see how we represent those operations. And if we want to be fancy and try and represent classical computation with matrix math, and we can always do this if we say that the 0 state means that the top element of our vector is 1 and the bottom is 0. And the 1 state is represented by a 0 at the top element and a 1 at the bottom. While we can represent those operations as matrix operations as well, not all of them will be available to us in quantum computing. The important thing to remember about quantum computing is that every gate has to be reversible. So given the gate that you want to perform and the result of its application, you have to be able to find the input that was passed in this operation. It's just how the physics works. So in matrix notation, you need to have the inverse of a matrix to figure out what the input was. And this means that the matrix itself has to be invertible. Now, there are some classical operations which are reversible, the ones which permute inputs, and there are some that are not reversible, those operations that either erase information or overwrite it. So you can implement the identity and negation operations, but you can't implement the constant 0 or constant 1 operations. For example, if you have a constant 0, while you know that the result of the operation is 0, you don't know whether the input was 0 or 1, so it's not reversible. You can't implement it in quantum computing. To highlight this, you look at the constant 1 cases down at the bottom, see how both arrows are pointing to the 1? With the result of 1, you just don't know what the input was. Now let's check out some gates on the unit circle and see how they operate. Identity and negation are reversible, as we just said. Their inverse is just themselves. So we do have their equivalents in quantum computing. The identity operation translates to the identity gate, and it has this nice diagonal matrix. And what it does to the qubit is basically nothing. It is convenient in a lot of mathematical representations in discussions of more sophisticated algorithms, but on its own, the identity gate doesn't really do anything. The negation gate, on the other hand, is one of the more useful gates in quantum computing. It basically swaps the top and the bottom elements of the vector. If you see the formula, you start off with C0, C1, and then you end up with C1, C0. We call it the bit flip gate. Why? Because if we use the Ket notation, we can see that it converts Ket 0 to Ket 1 and Ket 1 to Ket 0. Since we very often describe quantum gates in terms of their effect on basis states, it makes sense to describe it this way. It basically takes the basis state and flips it to the other one. If you look at what happens to the state of the qubit in relation to the red line, the state is pretty much flipped over that axis. This reflection is true for some gates, not all. It can be a very useful way to think about things. Now let's see some gates that exist in quantum computing, but do not exist in classical computing. Even if we didn't have anything like this, we were just limited to a subset. If we didn't have anything like this and we were limited to just a subset of classical operations, then it wouldn't be very interesting. You couldn't really do very much with quantum computation. The first gate that doesn't exist in classical computation is the most popular of all the gates. It's the Hadamard Gate. And it has this, this interesting matrix right here, h equals 1 over square root 2 multiplied by 1, 1, 1, negative 1. It's not a diagonal matrix, and it's not an anti-diagonal matrix. It has all 4 elements non-zero, which means that it takes a qubit in a basis state, which has its classical equivalent, and it puts this qubit into a state of superposition, in which both vectors have non-zero coefficients. It puts this one uses equal superposition. It's got states in which 0 and 1 have equal amplitudes, or equal amplitudes differing by 1 sign. So you can see that applying the Hadamard gate to the 0 state gives us a superposition of 0 and 1. If you were to measure the qubit at this point, you would have an equal chance of seeing 1 or 0. This is the basis of how the random number generator works, which we'll demonstrate later on. And applying the Hadamard gate to the 1 state gives us a superposition of 0 minus 1. So those 2 states are important in quantum computing. They occur in a lot of algorithms, and so they have their own special notation. They're called the plus state and the minus state. Remember that the symbol in the Ket notation is just a variable name. So the state is just state named plus. Another interesting thing about the Hadamard gate is that it takes a qubit in equal superposition state and it puts it back into the basis state. So we can transform both the basis states into the superposition states and the other way around. If we're going to make use of both of these properties today. Again, you can think about this gate as kind of a reflection across that red line, this kind of a 22.5 degree angle with the 0 state. And that contrasts only slightly with the bit flip gate, which is a reflection across the 45 degree angle. And the last gate that I'm going to introduce you to today is the phase flip gate. This gate is probably the least intuitive of the ones I'm talking about today, because it not only doesn't have a classical equivalent, but it also doesn't have a nice explanation, like it's a gate you use to put you in superposition. Rather, this is a gate which operates on the phases of the basis states. So it changes the sign of the coefficient that's attached to this state. So you can see it leaves the 0 state completely unchanged. Z0 is 0. And it multiplies the coefficient of the 1 state by -1. So if you apply it to the basis state, you're not going to observe any difference. We'll talk in a minute about measurements, and there's just kind of no way you can observe this change. But this gate makes a lot of sense when you apply it to superposition states, a state in which both 0 and 1 coefficients are non-zero. In those cases, you actually notice that something has changed in the state. If you apply the Z gate to the plus state, you get the minus state. From the minus state, you get the plus state. And we're going to make use of that property again later on today. And again, you can kind of think about this gate as a reflection across the horizontal axis. And yeah, there's some complex reasons why it's called the Z gate when things look here like a reflection across the x-axis. While the unit circle is a great tool for learning quantum computing, we're still kind of playing in the metaphorical kiddie pool here, and the reasons for that are beyond the scope of the talk. So this is a lot of information to take in, especially if you're not super familiar with matrix multiplication. So for today, those are going to be the only states that are shown on the circle. So let's sum up around these 3 gates. The X gate, the Hadamard gate, and the Z gate. You can see if you take the X gate, changes 0 to 1 and back to 0. You can see it preserves the plus state. And the minus state, it converts to the state with a different minus phase, so all the way to the other side of the circle. And the Hadamard gate converts the 1 state to the minus state and the 0 state to the plus state, and vice versa for all of these. Then if you look at the Z gate, it does a reflection across the horizontal line. So it really doesn't change anything about the 0 state. It converts the 1 state to the -1 state and converts plus to minus and vice versa. So the reflection axis is the horizontal. Also, the states on the opposite side of the circles differ by the coefficient of -1. It's called global phase and not a thing that you can observe. But in some cases, it's important. For today, it's not going to be that important. So you can assume that the points on the opposite side of the circle are just the same. Here's another state machine. It's just nice to have visual aids rather than do the matrix multiplication from scratch every time. This shows you just how those gates affect the basis 0 state, 1 state, plus and minus, and then how they move between each other. So how do they represent quantum gates in Q#? Since we discussed that we don't get access to the internal state of the qubit, basically it's not that convenient to represent operations as matrices every time you want to apply a gate. So we like to take an operational approach. We say that gates are just operations. They have a side effect of changing the internal state of a system. If you apply a gate to a qubit, it will not give you the output. It will not give you the state of the qubit after the gate, like this shows you. If you want a mathematical representation, you write Hadamard Gate multiplied by the 0 state equals this new state. In Q#, you just write apply H gate to qubit Q on line 6, and some gates will also have parameters. The internal state of the system of the qubit Q that we allocated here will change from 0 to plus, but that's not really represented in the code. It's something that we're going to observe based upon the dump machine output. And as you see here, that dump machine indeed shows us that the amplitude of both 0 and 1 states is just 1 over the square root of 2. So this is just what the math promised us. So we know how to allocate our qubits, and we know how to make transformations on their state. But so far, we didn't do anything that allows us to get information out of the system. And this is sort of important. Can't really have an algorithm which just kind of does something and never lets you know what it did. It's not really what algorithms are for. So how do we perform information readout in classical computing? In classical computing, it's actually very simple. All of your values computed during the algorithm are just normal numbers, 0 or 1. So you can just look at that value and read it, and nothing's going to happen from that act of you looking at it. In quantum computing, I mentioned once or twice already, the state of the qubit is not directly observable. So you're getting a lot less information out of the system than is used to describe it. And the second thing that absolutely has no equivalent in classical computing is that when you observe the state in quantum computing, it's not a passive action. It's an active action. You change the state by observing it. And the operations that we use to read information from the quantum system are quantum measurements. If you measure basis states, you might think that the quantum computing will actually still behave like classical computing, because if you measure the 0 state, you get 0. If you measure the 1 state, you get 1. And the states are not going to change when you do this. It's deterministic, just like classical computing. However, if you measure a superposition state, there's no equivalent in classical computing. And there's no equivalent for the measurement of the superposition state in classical computing either. So if you have this state with 2 non-zero coefficients, and then you measure them, you end up with a probability with the square of the amplitudes of the top and bottom elements. So let's say that we get a new qubit and then apply the Hadamard gate to it and read out that state. So you're in the plus state. It's an equal superposition between 0 and 1. And that means you have an equal chance of reading out the 0 state or the 1 state. You have a 50-50 shot either way. And more importantly, the qubit state is going to collapse to the corresponding basis vector. If you measure 0, the state of the qubit is now 0. If you measure 1, the state of the qubit becomes 1. The measurement itself is kind of sort of an operation on the qubit. And this is important because the coefficients C0 and C1 carry a lot of information, much more than just the 1 bit that you're going to get out of a system when you measure it. So when you measure a system, you're losing information, you're destroying the state. If you return to the bit and you try and measure it again, you can't get any more information about C0 and C1. You just get one shot at this measurement, and you get 1 bit of information out of it. So this is why quantum computing is sometimes described as drinking an ocean through a straw. You have this ocean of computational power, of the expressiveness of how you can represent the quantum states and the operations on them. But the way that you get information out of the system is just through a straw. You get one bit from each measurement, which means that we need to be very forward thinking and very precise when we write our algorithms. Measurements in Q# are very similar to the gates, except they actually have a return value. There are also operations that take qubits as parameters and change the state of those qubits as side effects, and then they return the value of the state as a result data type. For example, we allocate the qubit in the 0 state and then apply the Hadamard gate to it. Then measure the qubit. Once we get the result, if we look at the state of the system afterwards, it's not going to give us a superposition state any longer. It's going to give us the measurement result. In this case, it was measured to 1. And the state as a system is going to change to 1, which you see here in the image. All right, so we learned what qubits are, how we describe their states, how we change their states using quantum gates, and how we get information out of the system. And this is actually enough to get our first quantum application running. Let's look at how to implement a random number generator in Q#. So the interesting thing about random number generation is that there are 2 ways to generate random numbers. True random numbers are generated using some physical phenomenon, like tiny fluctuations of temperature or photons or something like that. Pseudo-random number generators don't generate true random numbers. They are mathematical constructs that give you numbers that are actually a deterministic sequence. It's just that it's a deterministic sequence in a complicated way, in a way that has some properties similar to true randomness. So for a lot of applications, pseudo-random number generators are perfectly fine. But for some of them, we want real random numbers. And in quantum mechanics and in quantum computing, measurement is such a fundamentally random thing, it's a source of true randomness. Because it's not some computation that brings us the measurement result, it's not a hidden variable that defines it. It's a proper physical randomness process. So if we prepare the qubit in superposition, in equal superposition, and we just measure it, it will give us a random bit, 0 or 1 with 50-50 chance. And here's the code that does it. We define a variable that tells us how many bits we want to generate. And if we want to count how many of them were 1s. So what we can do is allocate the qubit and repeat as many times as we want the simple process of applying a Hadamard gate to it. Put in equal superposition, and then we measure it. And that's basically what lines 4 through 7 do. And here we don't do anything with those generated numbers except we count them. So if the measurement result is 1, we increment our counter of 1s. And then we tell you here how many 1s we've generated out of all of the runs. In this case, we got, what, 52 1s? Something like that. And you can run this several times and you'll get different numbers. All right, so now we are going to hope and pray that my quantum random number generator kata works.
Don't worry, if it doesn't, it's my fault, John, because I was the one who did the PRs for the binder, right, for the kata. So gotcha. It's my PR that went sideways.
All right, well, give me 1 second here, and let's see if we can get something in. All right, if it doesn't work out, then we'll just talk through it. Nope, not working right now. Give me 1 sec. All right, so I'm gonna share again.
So I think maybe some people tried posting links and it got blocked or something. Maybe I can post it if you guys can send that in the chat.
Sure
in the Zoom
thing.
chat.
All right, so I'm going to just share this whole screen right here. And I think that's going to be the easiest way for us to go. Delbert, if you could post that link in the chat, that would be awesome.
Yeah, see, I'm sorry. I thought the chat was going to be in Zoom. So I'm not logged in to like Twitch or whatever it is. So
since I'm sharing my screen, I'll just post that link on here. It's aka.ms/try-quantum-katas-1.
Oh, cool. Maria posted the link.
Hey, good stuff. Good stuff.
That should come.
Okay. Yeah.
All right. So.
Great.
All right. So we're back. And here's the Jupyter notebook for the random number generation tutorial. And this is what everybody else will see if they're following along. Here we've got some introduction that kind of covers exactly what we just went over. It's talking about alpha and beta states and the amplitude of the states. Basically that the vector is a mix of the basis states, and when you measure it, it collapses the waveform to one of those basis states with the square of the probability of the vector, or of the element at the location on the vector. So we're going to go over basically the same thing that we went over in the quantum, or in the talk just now, is that you're going to take an operation on a random bit. You're going to assign a qubit to this Q variable. We're going to use the Hadamard gate as an operator on this qubit, which is basically that really cool matrix that we saw before of 1/√2, 1, 1, 1, minus 1. And then we're going to measure out that value. Usually this would work. I think I messed this up by inputting quantum measurement and then changing the int to a result. So then we're going to generate a random 2-bit number, which is really just kind of doing the same thing. Instead of using 1 qubit, we're going to loop over 2 qubits, or just do the same thing twice and then get out the measurement result. And then as you generate random numbers of arbitrary size, you can start stacking zeros and ones next to each other and then read that out into a larger number. So if you do it 1, 2, 4, 8, 16, 32, 64, 128, 8 times, then you'll have a random number somewhere between 0 and 127. So then after that, you can, so that generates, a Hadamard gate will generate probability with equal likelihood because it is an equal superposition of the 0 and 1 states. If you want to shift that a little bit, then you can generate probabilities using different states, right? So if you were to say go to a, was it 1/√3 1/2 element or superposition, then you would generate, I believe it's 2/3 of the time generate a 1 and 1/3 of the time generate a 0. And that's because on the unit circle, you've kind of got a little bit of a shift. It's not at that 45-degree angle anymore. Now you're at about a 60-degree angle. So that changes the probabilities that you would land at 0 or 1. And then I'll leave it to you guys to do this, generate a random number between min and max. So now if you want to take an arbitrary minimum and maximum, you could generate a random number somewhere between maybe 10 and 20. And that needs a little bit more massaging of the data and the code in order to get there. So that concludes my portion of things. I don't know if we want to do some questions now, or if we want to turn it over to Delbert to do his part and then questions after. But that's all I have for the moment.
No, I guess we could take some questions right away to see if there's questions that folks have on these particular binder experiments, in the binder environment. And then we can also take any questions that are about the first, John's first part of the talk. And then maybe we could give folks maybe 10 minutes to just try playing around with the notebooks on binder. Or if you've installed them locally and you're working locally, that's great too. And we could kind of combine a 10-minute break with a little lab period, and then jump right back in, or maybe just 5-10 minutes. Does that sound reasonable?
So I think actually a lot of people have been posting questions in the Twitch chat, and Maria has been answering them. So I think almost all the questions have been answered. Right. But let's see. Yeah. So if anyone has any questions like about the this exercise or any of the talk that John has that John was given, you guys can post questions in the chat, and I can ask them out loud to the speakers now. But if not, I think Delbert's suggestion that we can take a 10-minute kind of break / like play around time, that would be great. Okay, we have some questions actually. So okay, someone asked, do we need a Q-sharp compiler installed, or will we be able to just use the web-based compilers?
The binder includes the Q-sharp compiler. So the simulator, the quantum simulator, and the Q-sharp compiler, and there are also some other debug and trace statements you can run in the notebooks, and those are all supported in binder. So you don't have to install anything. That's the beauty of it, is folks could try some different things here today. If you haven't had any chance at all to play with quantum computing.
Yeah, it's very similar to the Jupyter notebooks that you would use if you're familiar with Python using AI or ML, anything like that. Very similar. You can run everything on the web. You don't need to have it locally. If you've got Visual Studio locally or Visual Studio Code, you can alternatively download these things. You get a lot of easy prompts these days. It's so much easier to set up Q-sharp and the Quantum Developer Kit than it used to be. So you can also go at it that way and run everything locally. And you're good on your laptop to simulate probably up to about 30 qubits if you got a decent machine. Any more than that, and you get a little bit of resource lock.
Okay, someone else is asking, is circuit visualization available in Q#?
You can use %debug for an expression, and that expression can be like an operation that's performing a series of gates and stuff like that, and it will generate the circuit for you. %debug, magic, the magic in the Jupyter notebook.
Okay, someone else asked, what's the max number of qubits supported by the Q# simulator?
It can support as many as you have memory for, and it's about, as John said, about a 16 meg laptop will get you about 30 qubits, and then as you can if you pop into Azure or something like that and get yourself one of those big beefy virtual machines and install the QDK there, you can get a couple more qubits. But that's it, right? Because each qubit you add, if you have n qubits, you need 2 to the n bits to represent the same information. And that's why quantum computing is so wonderful, but it's also why it gets really hard to get beyond 30, 40 qubits in a simulator.
Okay. Yeah. So I think someone else earlier asked, is a random number generator from like the simulations pseudo-random? And I think Maria already answered that, but they were also wondering, does that mean the random number generated by an actual quantum computer, like kind of more random? And I think the question is just in general, like, what are the differences between the pseudo-random generation and the quantum random number generation?
Right. So there's a couple things there. One is if you took this Q# program, you could change the provider from a simulator to either ion Qs, trapped ion quantum computer, or Honeywell's trapped ion computer and submit that to Azure Quantum, and you would actually get, yes, you would get a real random number. As far as like a non-deterministic number, because with any random number, generation process, it'll end up having a period at some point, right? You'll end up getting a more deterministic number, and that premise was what was behind the announcements that Google made, around quote unquote quantum advantage or quantum supremacy, so that actually the quality of the randomness that they were able to get, would take, depending on the debates and everything, would take, a supercomputing cluster years to give you the same sort of quality of random number generation.
Yep. And that's just a one-line change at the top of your code to that provider. It's really easy. So you write the same code. There's no reformatting that's necessary, refactoring, whatever. All you do is change the provider. Good to go.
Cool. Okay, someone else asked, so there are many languages right now to make quantum codes, and so what are, how is Q# unique? So what are some of the unique maybe features that Q# has?
Yeah, Q# is intended to be a native quantum language, as opposed to writing a kit in some other language that translates to it. So one of the things that makes Q# special, I think, is really around the notion of a difference between an operation, which is a quantum thing. You can operate at a higher level and say, I want to make that an adjoint operation, meaning reversible, and the machinery underneath the covers for Q# takes care of that for you. There's another very popular pattern where because you can't clone quantum state, right? You have a very common pattern where you go through a series of gate operations, and then you have an answer. You use phase kickback to push that answer into another qubit, like a holding qubit, and then you reverse these operations. And so that is encapsulated in a native command called within apply. So you can apply a series of these steps. So the intent behind Q# is to make quantum computing kind of more native, and we'll see in the next section how this notion of an oracle is really important, and oracles are easy to pass around in a native kind of functional programming language, and Q# it's a hybrid language, certainly, but it supports a lot of functional capability. And then, John, did you have anything else to add?
To add on, it's definitely a mix of C# and Q#. I would say that because it is a language that is specifically developed for quantum computing, that it's going to be more extensible and scalable as the language itself evolves, as the compiler evolves, as quantum algorithms and applications evolve. We're kind of building it from the ground up, just for with that evolution in mind. It's not like taking a library on, building a library on Python. Python's awesome, love it. However, it's up to each repository owner in order to kind of maintain that. There's not, Qiskit, besides Qiskit, I guess, there's not a lot of ownership of, there's no reason, there's no commercial interest in driving it forward, which really means that a lot of times things don't get done. We've all seen repositories go stale over time, that kind of thing. You got Microsoft backing Q#. It's going to be around forever, just like C# has been.
Okay, yeah. So I think we have some great questions and answers, but so I think we do want to take up Delbert's suggestion and take like a 10-minute break, because this is a 2-hour session, and so gives time for people to play around, go to the bathroom, get a drink of water, and things like that. So why don't we come back at 2, and then we can start with Delbert's next section of the talk.
Perfect.
Great. Thank you so much, everybody.
Okay, everyone. See you back in approximately 10 minutes. Okay, hello, welcome back, everyone. So for the next part, next hour, we'll have Delbert, who is the cloud solutions architect, data scientist, and quantum computing community leader at Microsoft, give us a talk. And again, we'll hopefully have some time at the end for questions and answers. So if you have any questions, please feel free to post them in the Twitch chat. We will also be answering some of the questions together with Maria from Microsoft in the chat as well. And again, if you have any questions after the talk, you're welcome to post it in the Discord channel, and we'll be going around there to help answer any questions there as well. Okay, so please, without further ado, please welcome Delbert. And so please take it over, Delbert.
Yeah, cool. No, I think we wanted to do one other bit of housekeeping really quick, and maybe let John take us through a couple of the answers, just the first couple of exercises, just so folks can see the magic, if that's all right.
Give me 1 second. All right. Okay, so I am in. So for exercise 1, generate a single random bit. First, we allocate the qubit, use Q equals qubit, and then apply the Hadamard gate to the qubit that we just allocated. Of course, in this line, it's in the 0 state. Here, it's an equal superposition of 0 and 1. And then we're going to, this is the measurement function. So we're going to measure the qubit. And if the measurement is 0, then we're going to return 0. And if not, we're going to return 1. And so that's how we generate a 1 or 0 with equal probability. So we put it in the Hadamard, apply the Hadamard operator, and then measure, and then have it come out the back end with either a 1 or a 0. So now that we've got that, then we can basically do the same thing. We can take 2 bits, and then we can generate a random number in the range 0 to 3 with the probability of getting the same equal probability of getting each of the 4 numbers. So same thing here. We take the qubit, and then we can apply a Hadamard gate to it. And then here, we've got a measurement of the qubit, and we can do let Q1 equals that. And then we can basically do the same thing. You can use another qubit. And then Hadamard on Q2. I hate live coding. Something always goes wrong. And then
Murphy's Law.
Right. Delbert Murphy's Law. And we're going to say let Q2A, I don't know, equal that. So then we just do our math here. So basically, we're going to say if the first one is a 0, then that only gives us the ability to have a 0 or a 1 in the on the other side, right? So if you imagine a 4-bit number here, let's say we have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and then, oops, doing too many bits. So we got 0, 0, 0, 1, 1, 0, and 1, 1. Those are our 4 possible states. So if we have the second, let's see. So if we have the second one go to 2, So if the first one is a 0, then we've only got 0 or 1 options for the second one. If the first measurement turns out to be a 1, then we have an equal possibility of getting a 2 or a 3 after the first measurement. So I don't want to write out all of this code, but
Yeah,
yes,
no.
you can look and see that if you've got the first one's a 0, you can either have a 0 or 1, and then you measure the second one, you get a 0 or 1, and then the second one is kind of the same thing.
So what you could do is you could return Q2A times 2 plus Q1. And that'll give you an integer, because the test is expecting an int to come back. So plus Q1.
Plus Q1.
There you go.
There we go.
That should do it.
Oops. Maybe unexpected code. Oh,
There you go.
Expecting. Maybe release qubits are not in 0 state. I got to measure. But that's the basic idea. I think if we use the other, what's it, M reset Z, then we should be able to return
You
it.
could do that. But yeah, I think that gives folks an idea for how the language works, and it gives them an idea on just how nice, you get answers right back. So you can try different things and see what effect they have as you're trying some different stuff out. That's perfect. Thank you, sir.
Yep, absolutely.
What I'm going to do is share my screen and then jump into the next part of the talk here. If I can find my Zoom here. Screen 2. All right. How's that? Can you see my screen okay?
Yep.
Okay, perfect. All right. So the next part of this, my slides will advance, is going into a common quantum algorithm called Deutsche algorithm. And if folks are familiar with agile computing methods, or maybe even extreme programming, if you're old like me, we used to say, do the simplest thing that can possibly work, as a starting point, and then you just kind of build up from there. And so from a quantum computing approach, the physicist David Deutsche came up with a magnificent way to have a sample problem that shows a quantum improvement. And so that's what the Deutsche algorithm is about. And then Dr. Jose came along later and extended this to multiple qubits. And so we'll show you a little bit about that. So to begin with, basically the question is, if someone gives you a black box, and your black box has one of 4 functions in it, these 4 right here: identity, negation, constant 0, or constant 1. If you've got any of those, if you've got one of those 4, how many tests of the black box would you need to show you whether it was a constant function or a variable function? And so in a classical computer, you need 2 queries, because you need to eliminate both possibilities. But it turns out in a quantum computer, you can get this with just 1 query to that black box. So that's kind of the crux of this particular algorithm. And so the first thing that comes into play is, what is this quantum oracle? How does it work? And so remember from John's part of the talk that any quantum operation has to be reversible. And we saw the constant 0 and constant 1 are not reversible. So we have to figure out another way to represent we have to figure out another function that we can work with that will let us test these things. And so in quantum computing, it's very common to have oracles that we use to set up a problem or work our way through an algorithm to find a solution to a problem. And so the person who's answering a lot of the questions in the chat, Maria, wrote this wonderful tutorial on learn.microsoft.com. If you go there and search on quantum, there's a graph coloring problem in there that she solves. And what you have to do is represent the nodes of the graph in an oracle. So that's really what we're doing with this particular problem is we're looking for a way to represent the problem so that the algorithm can operate on it. And in this case, what we do is we say, whatever our input state is, we're going to take -1 to the power of whatever f of x is. So this is x is our input vector. And we're going to take -1 to the power f of x and multiply that by our x that was given to us to begin with. So this represents, this oracle is reversible. And so that represents the problem. That is the way we can encode those functions so we can solve them quantumly, okay? So if f of x is equal to 0, then of course it's the 0th power and -1 to the 0 power is 1. If f of x is 1, then we multiply the phase of our output by -1. And so this defines the oracle. And what we can do here is show you a couple of examples. So if our function is constant 0, if we decide that's what we want to do, then the oracle needs to be in this form here. So what we do is we say, okay, if we apply the oracle to the 0 vector, 0 state, we should get 0 back. And if we apply if we apply the vector to 0, what happens is we take -1 to the 0 power, which is 1, right? And we multiply that by ket 0 and we get 0. If we take ket 1 and pass it into this function, then it's -1 to the 1. And so ket 1 then becomes, that should be -1 to the, oh wait, I'm sorry, because f of 1 is 0. So it's -1 to the 0 power. So that's also 1. And so that gives you ket 1. So representing this function here, constant 0, in our oracle means we need the identity gate because we need 0 to map to 0 and 1 to map to 1. So the identity gate, the I gate that we saw before is what we would use as the oracle. Now, if we have the identity function, right, that's this one here, the first one over here in our possible black box list, right? 0 map to 0, 1 map to 1. So what happens then? So we take the x is 0. We take -1 to the f of 0. And that gives you, so -1 to the 0 power times ket 0 is still 0. And then this time though, if we take 1 and f of 1 is also 1. So -1 to the first power is 1. I'm sorry, it's -1. And so then that gives you the negative ket 1. And this, of course, was the phase flip gate that we showed earlier. So then the oracle that reflects the identity function is the phase flip gate. And you would do the same thing for the constant one and for negation. So those give you a C0 gate and one of the other gates. So that's or actually a combination of C0 and X. So those are the oracles that we have. And so then if we look at the algorithm itself, it's actually a pretty simple algorithm. We start with our qubit in a 0 state. We apply the Hadamard gate to that state. So we put ourselves in an equal superposition of 0 and 1. And then we apply this oracle UF. And if we have a constant function, so f of 0 and f of 1 are going to be the same, then we end up with a superposition where the phase is +1. But if we have a variable function, in other words, f of 0 is not equal f of 1, then we end up with a negative phase in our state. And if we apply the Hadamard gate, remember from John's part of the talk again, if you apply the Hadamard gate to the plus here, you get 0 back. And if you apply it to the negative phase here, then you get a 1 back. And so the idea then is your qubit, your final qubit answer, you measure it. And if you get a 0, you end up with your oracle was a constant function and a 1 for the variable function. Okay, so that's the way that you can use just one query instead of 2 queries to get this answer. Okay. And so in Q#, the way that looks is you end up, again, going back to use a qubit, apply the Hadamard, apply the oracle, apply the Hadamard again, and then measure. And the key here is that these oracles are first class, they're operations in Q#, and they're first class citizens that you can pass around as functions. So if you're familiar with F# or Haskell or some of those languages that are functional languages, then you'll get the idea. You can pass these functions around as first class citizens. So in this case, the oracle itself is just something we do to the qubit, and it answers unit. You know, unit is the Q# equivalent of void in C or C++. So that's the key to these oracles, is that you can pass them around and operate on them in Q#. So let's go ahead and jump into what we're going to do now is use these unit circles and just see the difference between what happens with a constant function and what happens with a variable function, you know, oracle, as the oracle. Okay. So we started out in the 0 state, right, which is 1 on top of 0 here. And now we apply the Hadamard gate and we get this equal superposition. So we've got our qubits ready to go, and there's no difference so far, right? But here's where the difference occurs. We apply the oracle. And if we apply the oracle to the variable function, right, the non-constant, then we end up with either the -1, we end up with an equal superposition, but we end up with either the phase of either -1 in the top basis state or -1 in the bottom basis state. And if we apply it to the constant function, the identity gate, remember, was one of those oracles, so we don't really do anything to that. And then the other one was negation. One of the other ones is changes the sign on both basis states. Okay, both both components of the vector. Let's put it that way, of the state vector. And so what happens now, if we apply the Hadamard gate again, here we go. We've got the constant function ends up being either 1 over, it ends up being the 0 state, right? The constant function, because it's the -1 there doesn't matter when we measure, because it just squares that. So we can't see the difference between the -1 and the +1. But over on the variable side, you see we're ending up with 1 with state 1 instead. So that tells us our answer. That's how we distinguish between the constant and the variable function. Okay. So now if we look at it, we can extend this to n qubits. So if we had 100 qubits and our black box, our oracle, was guaranteed to be either constant or balanced, we would still only need 1 measurement in the quantum case to get the answer. Whereas we would have to measure 2 to the n-1 plus 1, right? Depending on because the first 2 to the n-1 queries could return 0 even in the balance case, for example. So that's how how you start to see the power of what we can do with quantum computing. And this is a very common pattern we'll see, where you put your qubits in a superposition state, and then you work with them. And as you work with them, you nudge the probabilities in the right directions, so that when you measure, you're going to get a good answer. And so in this case, the algorithm itself is very similar to the Deutsche algorithm, right? You start with n qubits in the 0 state. You apply a Hadamard gate to each qubit. So there's a Q sharp. Folks were asking, well, what does Q sharp give by me? Well, Q sharp has a function that lets you pass more than 1 qubit, each qubit through an individual gate. So that particular function may help you out in the exercise here in just a second. And so then you apply the Hadamard gate to each qubit. You apply the oracle to the register of qubits, we call it, the group of n qubits. And then you turn around and apply the Hadamard gate to each individual qubit again. Then you go into a loop and measure each one of your qubits. And if any of the results are 0, the function's constant. Otherwise, it's balanced. Okay, so that's the algorithm. And what we can do is jump into Binder and give that a try. So again, this is the exact same link that Maria had posted earlier. You can go into akams.try quantum katas 1. And if you were in Binder for John's exercise and you haven't been playing around in there while I've been talking, which either way is fine, but if you left it idle for a little while, you may have to refresh the page to have Binder come back. So obviously it's a scalability thing, right? If you've got millions of people using binder.org, they don't give you very much time before they time out, so that you can save resources. So anyway, that's the important thing. And what I'm going to do, I think at this point, is I can show you when you go to the main. I'll just show you here. When you go to this main Binder page, it'll be under the quantum oracles and simple oracle algorithms. You click on exploring Deutsche Jose algorithm tutorial. Okay. And then I'll show you in there which one of the exercises to work on. So give me just 1 second. I think I can stop here. Okay. So now this is my local, I'm just running this locally, but if you look, there are some really cool, with all of this, they kind of take you through the math, and these other exercises are more classical to kind of get you warmed up. So we're going to skip those, and we're going to skip the oracles. This particular exercise 4 will give you the oracle. The oracle calls are being passed into you as part of a test, okay, like a unit test. So what you can do is go to the 4th kata, the actual quantum algorithm, and you need to fill in this variable and then fill in you want to use for an array of qubits, and then they give you the logic here that you want to do. So the first thing you have to do is you have to apply the Hadamard gate to each of the oracles in X, or I mean each of the qubits in X. Then you apply the oracle to X itself, and then you apply a Hadamard gate again to each of the X's, each of the qubits in this register. And then finally, you go into a loop and measure each qubit. And when you measure the qubits, then you kind of keep a tally, because if any of them is 0, then what you need to do is you need to set the is constant to false. And so that's how you'll get your answer, and then you can just return the answer. So
Albert, I think, sorry to interrupt, I think some people have trouble seeing because the page is quite small compared to the whole screen. If you could maybe zoom in a little bit.
Sure. Yeah. Let me do that. I'm using my lower resolution monitor for this just to make it easier to see. And then, so that should, I'm sorry there, that should give you a better look at it. So it's this 4th exercise, and there's a lot of cool stuff. I mean, obviously there's a ton of different exercises to try out. There are all of these different kata, but this is one that you can kind of come back to, and there's videos to watch up above here about some more of it. But anyway, for this particular thing, this is where we're looking to fill in, and I have 29 minutes after the hour. And we still want to cover a little bit about multiple qubit states. And we'll spend just a few minutes on that, but that should give everyone the foundation that we need for the exercises and challenges that follow for the rest of the week. So that's why we want to make sure we set aside a little time to do that. But if folks want to take a few minutes now and give a try at this particular kata, maybe we can take just maybe, yeah, 10 minutes, 5:30. Yeah, or I have 5:30, I'm on Eastern time. And so if we want to take maybe just 5 minutes or 7 minutes to give this a try, kind of see what you can get going in the environment, and then we can come back. Yeah, let's make it 10 minutes. Let's make it so I have exactly half past the hour. Let's go until 20 minutes till the hour. And we'll take it from there.
Okay, yeah, sounds good. So I guess we can reconvene at 5:40 Eastern time, or 2:40 Pacific time.
Perfect. All right, folks. I have about 20 minutes till the top of the hour. So let's jump in. I'm going to go ahead and go through filling out this answer. And then what we can do is jump into some discussion about multiple qubit measurement, and then still have some time if there are questions in the chat that I should address broadly verbally. We can do that too. So anyway, let's jump into our Deutsche algorithm here. So we're given capital N, it's an int, which is the number of bits, and we're given a function called oracle that maps an array of qubits to unit, which again is void. So, and then we need to return a Boolean from this function. And so the testing framework is looking for a Boolean answer as to whether it's constant or not. All right, so we're going to start out with setting our is constant to true, and then our array of qubits. That's pretty easy, right? We just put n in there, and that'll use n qubits, whatever that is. And very important, we're guaranteed that our qubits all start out in the 0 state. So we like that. So then if we're going to apply the Hadamard gate to each qubit in that register, the function we can use is apply to each. And if you're a functional programming fan, I believe that if you look up the implementation of this, it's a partial function application. So anyway, here's the what we're going to do is we're going to apply the H gate to each qubit in X. So there we go. And need a semicolon. All right. So then that's applying. Now we need to apply the oracle or invoke the oracle on the register. And so that's really easy because this is a first-class functional language. So we just say, apply the oracle to X. And so then what we need to do is we need to do this again. So copy paste, right? Everybody's friend. So we're going to apply that each again. And then what we have to do is we have to loop through our qubits in our register and test, measure each one and test it. So what we're going to do is we're going to say for, and then this is just like many languages have this now, for Q and X. And then we're going to go ahead and say if, and now what we need to do is we need to measure. So that's the M operation, right? Just like we did before. And so we're going to say MQ equals 1. And 1 and 0, see the blue syntax highlighting here. 1 and 0 are reserved for the measurement states 1 and 0. So they rather than integer 1 and 0. So we kind of have to convert, we had to convert in the other one with that question mark binary operator. Here, what we're going to do is if it is equal to 1, then that means that we have a balanced function, right? So we would set is constant to false. And again, the thing that you'll see is you need to use the set syntax, because in a functional language, generally your storage is immutable. So we want to explicitly set the variable to something. So then what are we going to return? Well, we've done all this work on is constant. So if I could spell, then that should do it. And the nice thing, of course, about my poor spelling is as long as I'm consistent, I consistently misspell my variable names, they'll still compile. So let's see here a second. Oh, come on. I think let's run the cell. Whoa. Kind of moved on me here. All right, so I ran this cell, and so it tests with f of x equals 0, f of x equal 1, and then the two variable functions, and success. So that was a correct that was correct test. So we passed the test. All right, and so now what I'm going to do is I'm going to jump for a second into multi-qubit states, and then we can have some question, do a little bit more question and answer if there are any questions left. So where's my PowerPoint here? All right. So now what we're going to do is we're going to scale up to multiple qubits. We're not going far, just 2 qubits, but what the heck. All right, so here is classical bits, right? So if I've got 2 bits in memory, they're next to each other, and I have these states. And this is again that vertical, this is just a column vector here. And so the column vector 0, 1, and then 0, 0, 0 is the state 0, 0. Here it's 0, 1, 1, 0, 1, 1. Okay. And then if we have multiple qubits, this button here, then the qubits themselves, right, have that similar column vector notation. And remember, though, that when we're talking about these 2 qubits together, the sums of the absolute values of these complex numbers, the sums of the squares of the absolute values of these complex numbers need to add to 1. So that's the constraint that comes along with quantum. So then if we look at how to compute states, we just use the tensor product. So in this case, if I take the tensor product of 2 zeros, right, of 2 ket zeros, I've got 1 0, tensor product 1 0. So 1 times 1 is 1, 1 times 0 is 0, 0 times 1 is 0, and 0 times 0 is 0. So we end up with 0, 0, 0, 0, which can be shortened to just this kind of condensed notation of 1. And then if we have 1, 0 and 1, if we're combining 2 states, 1 and 0, we have the tensor product of them. And so we go through that same exercise again. And this time we end up with 0, 0, 1, 0. So that means, and this is a big endian notation here, right? So this pair of parts of the state are 1, and then the other is 0. So this could be the 0th place. This is the 2's place. So then you could represent that with a 2. So like a 3 here would be 1, 1. So that just a little bit different. And then the other, yeah, so the tensor product is, I kind of just stepped through that. And then the other thing to keep in mind is that with these multiple qubit states, the qubits can be separable or the qubits can be entangled. And so this is a completely different kind of another level of the quantum mystery. And so if you have separable qubits, then you can write them as a tensor product of individual states. So in this case, Alice and Bob both have simple, their qubits are separable because you can write them as the tensor product of these two states. But this state here, called the Bell state, is not, it's entangled because you can't write this as an individual tensor product of these two things, which means that the measurement is going to be correlated, between these two qubits. And I think there are scientists now who have entangled photons and bounced one of the entangled photons off of a satellite. And at that particular distance, if you measure one, it's a 0. Well, that means the other one has to be a 1, and vice versa. Okay, so that particular spooky action at a distance, as Einstein called it, is another feature of quantum computing, and we use entanglement in quite a few algorithms as well. So that's what I had prepared, and I want to point out that there are a ton of ways to learn more about this stuff. To the Q# language is open source, the QDK is open source, so you can jump in and contribute and work with Azure Quantum, which is now in preview, sign up. And so there are a lot of different things to kind of take further and study and work through things. So I wanted to make sure you saw that too. So then with that, I think I still left a few minutes for more questions, if we have more questions from folks.
Okay, yeah, so if you have any questions for Delbert, please post them in the chat. I think there were a few questions that were ongoing, and Maria was answering some of those. Let's see, so. Okay, we're getting some questions now. Can we run the program on a hardware? I'm guessing that means, can we run the program on actual quantum hardware?
You can. I don't think there are any ways, usually with Azure, with most things in Azure, you can sign up and there's kind of a free tier of the service and things like that. Our simulator is kind of the free tier. So if you want to use real quantum computers, you certainly can. But you're going to have to get a little budget allocated to paying for those. So there's actually the details are on the Microsoft Azure website. So if you have like an NSF grant or something, and so you have some money in there, maybe you can, you could sign up and work with the quantum computers.
Okay, another person asked, can you please summarize the difference between a gate and an oracle? So I think they're just confused on what each one of them is doing on the quantum state.
Right. So So the gate is the fundamental kind of unit to change state. So we saw a few, the Hadamard Gate, the phase flip gate, and so on. So those are the 2x2 matrices, or there's some other gates that we'll see later in the week, perhaps, that actually work on a couple qubits at once. So you could use a controlled NOT gate, for example. So those are to set our qubits state. An oracle is made up of gates, and the oracle is a function that we use to put our qubits in the correct state to operate on them, to have the algorithm operate on them. So the oracle defines your problem. And so one thing you can see a lot of, and you can see in that Microsoft Learn module, is if you can express a problem using the oracle, then you can use, and it's what we call a phase oracle. You can use Grover's search to find, to very quickly find the answer to that particular problem. And so, and there's Q# and the QDK make that really easy, because there's like a Grover's search function. So you just import the darn thing and apply it to your oracle, and you will have solved your problem. So that's about the best way I can think of explaining those differences.
Okay, I think someone was also asking, if Microsoft has any opportunities. I think this is something that a lot of the students in the chat would be interested in as a general kind of question outside of these technical stuff. I guess, yeah, if you have any kind of like what kind of opportunity for students that Microsoft is offering in terms of like internships or like kind of like study work combination programs and things like that. I don't know if you have any kind of suggestions for the students here.
We have internships and have I think we have a whole quote unquote class, a whole group of interns who come in each summer and work with us, and some of their exploits are quite famous inside, at least inside of Microsoft. And so we're delighted to have folks apply for internships. I think especially because of COVID and having to do a lot of coordination, the internships for this summer are already closed. So you kind of have to watch and watch for next summer. Maria, who's been answering a bunch of the questions, actually has a Q# blog entry on internships in the quantum kind of space. But yeah, there are all sorts of different, we had someone last summer, an intern last summer that I was working with in Microsoft Research, who was working on weather prediction. So even if you're, if you're into atmospheric science, or if you're into, other things, there's a ton of, I'm hoping there's an internship that would appeal to the scientific discipline that you have. And so, yeah, it's Microsoft.com/career, I think singular, that you can go and look, and they have kind of two. The first question they ask you right there is, are you a student looking for internship, or are you a person who's been working, in the profession for a while? And so that would get you right into that branch.
Awesome. Yeah, I think we're just about to run out of time. So please let's thank Delbert and also John for the wonderful talks. And please, book your times for the slot on Thursday for the other Microsoft technical talk from Maria. So if you're interested in doing the Microsoft Challenge, please, of course, head to that talk as well. And yeah, we look forward to seeing more of you guys in the hackathon and participating in the challenges as well. So I guess, yeah, we can call it a good session, and I'll end the session now. And of course, if you have any more questions, you're welcome to post in the Discord channel, and we and Maria and others will be hanging out to answer some of the questions if we have time. Yeah, thank you very much.
Perfect.
See you guys later.
Thanks, folks.
Thanks, everybody.